we're now ready to talk about the basic operation of our MOSFET. So in order to do that, we're going to consider an enhancement mode device with a p-type substrate. So really we have sort of 4 iterations, right? We can have enhancement mode or depletion mode, and we can have a p-type or an n-type substrate. So in this case, we're going to consider enhancement mode, p-type substrate. Now remember, our enhancement mode means that the device is normally off, or in other words, there is no inversion layer without a gate voltage present. So what we can do is we can sort of think about what's going on at these 2 interfaces. So we have our simple 2D diagram here, and between our source and drain regions and the substrate, we see it essentially as like a p-n junction diode. So we can say with no gate voltage, so with no VG, we basically have 2 back-to-back diodes. So 2 diodes, and they're back-to-back, so they look something like this. So we'd have our P region and our N region, and this would be our source. And then this goes through our substrate, which is also connected over here to our drain. And so of course we could see in the ideal case, we have no current going through that circuit. So ideally no current. In practice, we'll get some small amount of current, but essentially nothing compared to when we turn this device on. So how do we turn this device on? Well, of course, if we get a large enough gate voltage, we're going to have an inversion layer. And we'll come back and talk a little bit about what is large enough in a minute. So large enough gate voltage is going to create our inversion layer and turn on our device, or allow us to form a channel that connects our drain and source regions. So let's copy that 2D figure down here. And now let's say we've applied some positive voltage to our gate. And so in doing so, we create this inversion layer. And because this inversion layer is in a p-type material, remember this is going to be an inversion layer of electrons. So now we have this channel of electrons that is allowing our majority carrier electrons in our N regions of source and drain to sort of go back and forth. So a quick note on our terminology is, again, we have this channel of electrons that's allowing current to flow, and we see we got that for a p-type substrate. So if we have a p-type substrate, that gives us a channel of electrons. And so what we'll call this is, we'll either call this an N-channel MOSFET or an N-channel device, or oftentimes you'll just heard this referred to as NMOS. So let's change that back to yellow. So NMOS or N-channel. And so similarly, we could say if we had an N-type substrate, then from what we talked about with our MOS capacitor, we know we're going to have an inversion layer consisting of our minority carrier holes, so channel of holes, which means we're going to have a P-channel device. Or you'll also hear that referred to as PMOS. So again, just a little bit of terminology there. So now that we have this inversion layer, we can talk about applying a voltage between our drain and source. And so typically we said our source is going to be grounded. So what that means is if we apply some drain voltage with respect to the source, if that value is positive, it's going to be causing electrons to flow from the source to the drain. So if this guy is positive, greater than 0, and let me get rid of some of our, well, that didn't work. But basically we can see that if we have positive charge here at our drain, that's going to be attracting electrons. So we're going to have electrons that are wanting to move from the source to the drain. And so that's where we see our notation comes from. So our source is acting as a source of electrons, and they're being drained in our drain terminal. Now, of course, that means our conventional current is going to be flowing in the opposite direction. So it's going to be entering the drain and leaving the source. Excuse me. So through all of this, we've sort of assumed some ideal conditions. We've assumed we have no current going through our oxide. So we're assuming this is 0. And as we said above, we're also assuming 0 current in the substrate. So ideally, no current in our oxide or in the substrate. And so of course, realistically, we are going to have some non-ideal effects. We're not going to consider those here, at least in terms of oxide and substrate leakages. But as you get sort of into more detailed courses about this, you would learn more about that. So one thing I want to mention in terms of our oxide current, we've talked before about how these devices are continually being scaled down and made smaller. And so in doing so, in order to keep everything sort of scaled appropriately, that means that this oxide thickness also has to get smaller. So intuitively, what we can realize is that if that oxide is getting smaller, it's becoming less and less resistant to current flowing through it for a given voltage. So that poses a problem because we don't want to have currents going through our oxide. And so one solution to that in sort of more modern, smaller MOSFET devices is to use something called high K dielectrics. And so our high K dielectrics are just dielectrics which have a larger dielectric constant or larger relative permittivity. So dielectrics. And so for instance, in a classic device, this oxide layer may be something like silicon dioxide, but in more modern ones, it's going to be something that has a higher dielectric constant. So now let's revisit that idea of what gate voltage is required to turn on the device. So how much is large enough? So we have a special name for this voltage, and it's called our threshold voltage. So gate voltage required to turn on our device. And so in this case, it's going to be required because we said it's an enhancement mode device. It's normally off. And so again, we're going to call this our threshold voltage. And so we're going to refer to this as VTN. You'll see it written differently in different texts or in different places. Sometimes you'll just see it as VT. Here, we're going to avoid that so we don't cause confusion with our thermal voltage. Also, you'll sometimes see it as V sub TH, but of course then you can have confusion with our Thevenin voltage. So ultimately you want to look at the context to determine which type of voltage the symbol is referring to. So the definition of this is somewhat arbitrary, but it corresponds to something called strong inversion. So remember when we were talking about our modes in our MOS capacitor, we said there's 3 modes. One of those was inversion. And so typically, actually, if we think about it a little more, we could define our inversion in 2 sort of subgroups. One of them is weak inversion, and one of them is this strong inversion. And so that transition into strong inversion is where we say our device is turning on. And so just real briefly what that is of course we have some concentration in this inversion layer of electrons. And so our strong inversion or our threshold voltage level is when the concentration of these electrons in the inversion layer is the same as the concentration of our holes in the bulk semiconductor. So again, not something we're going to be concerned about in this course, but just something to be aware of. The one other thing I want to point out that we mentioned earlier is typically our source and substrate are going to be tied together. So for instance, if we deal with this substrate terminal, typically we're just going to tie that to ground as well. But more often than not in this course, we're going to be ignoring that substrate terminal.